We'll speak about the Verlinde formula for Higgs bundle moduli spaces.
So I thank you for inviting me here to participate in this very nice conference. I've enjoyed the talk so far. It's been really, really nice. So let me just try to set the scene for the old Verlinde formula, just to remind you. And I've just, at the same time, I can sort of set the generality that I will be looking at. So for me, G is going to be a symbol and simply connected complex Lie group. So, well, complex algebraic group, if you like. So I'm going to use this letter for the Lie algebra of G, so just Gothic G. I'm going to pick a level. So all these theories come with a level, which is a non-negative integer, k. And then it also comes with an associated label set. And in order to define a label set, I just have to do a little bit more fixing of notation. So this here is going to be the killing form. And it's going to be normalized. Maybe I do it like this since it's complex. So it should be normalized in such a way that if you look at the longest root, it has square root of 2 as its length. So theta is the longest root. And then this label set here, well, it is simply just the set of integrable highest weights. So integrable highest weights, such that if you look at the inner product between theta and lambda, this is in between 0 and k. So that's the finite label set that the theory comes with. And then what I'm going to be interested in is you also fix a curve. So x is a complex, smooth algebraic curve just over the complex numbers. So if you like, a Riemann surface. And I'm going to use, in a second, so I might as well introduce it right away, sigma. This is going to be the underlying smooth two-dimensional manifold. Okay, and then what I'm going to consider, and I'm going to give you not a definition right now, but I will give you an alternative definition in a second. So don't worry if you don't know about this, but I'm going to let this here, so we're using the Tsuchiya-Ueno-Yamada notation, so V dagger sub G, comma lambda, comma x, and I guess I need a little bit more, so x vector simply just going to be x1 up to xn inside x, so n disjoint points, or distinct points, and I'm going to pick lambda, which is a labeling of each of those points, and then the Tsuchiya-Ueno-Yamada rational conformal field theory construction gives you a well-defined finite dimensional vector space associated to the curve x, the points, and these labels from this label set. So this is a finite dimensional complex vector space. Okay, and so the Verlinde formula is simply a formula for the dimension of these spaces. Well, actually, of course, Verlinde came from physics, and so he worked in a general rational conformal field theory setting, but I'm just going to give you, actually the formula I give you actually holds in general, but I just want to focus on this particular case, because this is sort of mathematically well defined. So it says the following. So in order to specify what that formula is, I need a little bit more of data. So what you do is you consider this theory here when x is an elliptic curve. Oops. So when the genus of x is 1, so you have some elliptic curve, then what happens is that if you look at this vector space associated to G and no mark points and no labels, therefore, of E, then you can actually write this as a direct sum, so it has a kind of preferred basis. So you write it as a direct sum where you run through all the labels, a copy of the complex numbers times a basis vector for each of the labels. And so this elliptic curve has an automorphism. Let's say that it is such that it has precisely the following automorphism. So if you look at the usual, one of the generators, the S matrix, inside SL2C, which is the mapping class group of this genus 1 Riemann surface, genus 1 surface. But if you pick the elliptic curve exactly such that it has this automorphism here, then of course that will act on this space here because it's naturally associated to it. And so there is some action of this guy here, which I'm going to represent, now that I have a basis for this space here, simply as some kind of matrix. And so, for example, if you take G equals to SL2C, so the sort of basic example here, then the label set at level K is simply the integers for 1 to K. And this S matrix in this case here, so lambda mu here, this is just square root of 2 over K plus 2 sine mu plus 1 lambda plus 1 pi over K plus 2. So that's the specific S matrix that one gets for that theory. All right, but in general there is an S matrix associated to any of these theories here, and the Verlinde formula, and so in the way that I'm presenting things right now, it's actually a theorem due to Toshiya, Ueno, Yamada, who proved it first in exactly this formulation here, that says that the dimension of the space here, x vector lambda, sorry, did I put them down there? I didn't mean to double the notation. So maybe I just say that this theory depends on G here, but the information is in there. So applied to, of course, this is any x, not just this particular x, any number of punctures and any labeling you want. This here is a sum over the label set, and then you get S mu lambda 1 up to S mu lambda n, and then you get divided by S0 mu, and then you get 2g minus 2 plus n. So this is the classical Verlinde formula. You see that the S matrix, for example, for SL2C is this. So it is not obvious that that thing is an integer. In fact, it took the genius of Don Zagier to just start with this expression and prove that that is an integer. But actually, it turns out that this is a polynomial in K. Okay, with rational coefficients. All right, so now let me tell you the context in which this Verlinde formula nowadays sits. And so if I start here by having this guy here again, then what sort of made a lot of algebraic geometers very interested in this. So this here, the definition of this is algebraic geometry, but it uses infinite dimensional varieties, so int varieties and things. So it's a little bit complicated. However, there is a very finite dimensional alternative for this. So there is actually a parabolic moduli space that I'm just going to call P for now. And there is a line bundle over this. So this is a compact algebraic variety. This is a rank 1 invertible sheaf on that variety. So that renders this definitely finite dimensional. So that's a proof that this is finite dimensional if you believe this isomorphism here. And so this here was something that people really wanted to try to compute dimensions of these H0s of these moduli spaces. And all of a sudden, there was a complete answer from physics. Now, this theorem here, this is due to Bouville and Laszlo. And in the parabolic case, so I'm lumping everything together, this is due to Pauli. Okay, now there is a way to take these here, which actually form vector bundles over Teichmuller space. They have projectively flat connections. There is a way to twist these bundles by a one-dimensional theory in such a way that you get flat vector bundles over Teichmuller space. The price is you have to go to a central extension of the mapping class group, but all of it fits wonderfully into what's called a modular functor in the sense of Kevin Walker. So you actually get from this a modular functor. So let Vg of sigma. So now it only depends on the surface sigma, and of course still the points and the labels. So this here is a modular functor. And so myself and Ueno, so Andersen and Ueno, we have made this construction here for any g of this assumption here. And then what we have proved is that this modular functor here, in the case where g is glnc, this is actually the same as VWRT k of sigma x lambda. So this is the 2D part of the WRT TQFT, so the Witten-Resittigen-Turaev invariant. And I mentioned this because many of the other talks that we saw yesterday was indeed about connecting up to the Witten-Resittigen-Turaev invariant. And so this here, so Verlinde formula for this actually is the Witten-Resittigen-Turaev invariant of the surface cross S1 via this. And so this isomorphism here is also due to Kenji Ueno and myself. So this is sort of a nice picture. Here it turns out, so this isomorphism here is really an isomorphism where you take into account actions of mapping class groups. So that tells you, so the two-dimensional part, when you really remember mapping class group actions and everything, that completely determines the TQFT. So this is telling you that if you want to study the representations of the mapping class groups of the Witten-Resittigen-Turaev invariant, you're actually allowed to use any of these four pictures as you like, because they're all isomorphic. Okay.
How does this relate to Axel Singer and Witten on geometric quantization of Shinsen?
It relates to that in the case when you have no parabolic points and you look at SUN, or S, well, as I formulated here with the complex group, SLNC, they produced a connection in the vector bundle that you see here. Because this here depends on an algebraic structure, so a point in Teichmuller space. So this is really a bundle over Teichmuller space, and it has a projectively flat connection. They constructed that connection. And it was also constructed by Nigel Hitchen, and I have proved that the two connections are the same. Okay. Yeah, so there are many more things to say about that, but that's not what this talk, I mean, this talk is not about that sequence or isomorphism. Because what I want to do now is do something new. Because in some sense, this is considered well-known and old theory, and we have that fairly well under control. So what I want to do now is actually try to generalize this. But before I do that, I want to give you an alternative formulation of the Verlinde formula. And this is, yeah. So this is really following Tillemann and Woodward. Okay, so yeah, maybe I should just say at this point here that almost until Tillemann and Woodward, all of the proofs that were known of this theorem here was of the following type. You take this vector space or any of the models that you want, and you prove that the vector space satisfies a certain factorization when you factor the curve. So when you degenerate the curve into a nodal curve. You prove that it behaves well, you resolve the nodes, and then you degenerate everything into P1s with 3 marked points, and you determine what the dimensions are there, and you can prove this formula from that. So I'll tell you what the Verlinde algebra is in a second, which is indeed given from this pre-point function. But the first proof that didn't go this way was actually done by Tillemann and Woodward. So let me just show you this now. So I'm now going to switch to no mark points for a second. So I'm going to say that let M be the moduli space of semi-stable holomorphic G bundles on X. So X is our Riemann surface of genus G, or if you like, a smooth algebraic curve over the complex numbers, and I look at the moduli space of semi-stable holomorphic G bundles. So this here is a nice projective variety inside some large projective space. And so I'm going to let L be the determinant bundle on M. So the Picard group of this moduli space is a copy of the integers, and this is a generator, an ample generator. And so therefore, the Verlinde formula, so therefore this here, you can take this to the kth power, that was a k, sorry, and this here is a finite dimensional vector space. And so if for no mark points, that's actually isomorphic to this by what I wrote up there. So that's the parabolic moduli space. When I don't have any parabolic points at all, then that's just the standard moduli space. Okay, so now a little bit more Lie group setup. Maybe I should do the Lie group stuff over here. I'm going to let T inside the Lie algebra be the Cartan. And I'm going to consider the following map from T to its dual, which is simply just the following map. It's just given by this killing form, but I scale it by k times h, and h is the dual Coxeter number. So then what happens is that this actually turns out to cover an isogeny on this torus here if you look at the exponential maps here. So you get an induced map here from just looking at this map here from the Lie algebra to its dual. And what I want to do now is I want to let f be the kernel of this map chi. I am going to take rho to be half the sum of the positive roots, like this. I am going to let f rho be chi inverse of e to the 2 pi I, this Weil vector here, rho. I also need delta of f. This is simply just product over the positive roots also, and then you do 2 sine I alpha over 2 applied to f. So this is for f running in T. I think that suffices. So the dimension formula, so theorem, and I think I'm going to stick here to initials. So the names that goes with this is the following: Senes, Bertram and Senes, Donaldson, and I try to do them in the order that the papers appear. I might make mistakes here, hopefully not. Doskalopoulos and Wentworth, Kumar, Narasimhan and Ramanan, Faltings, Telemann, and then Telemann and Woodward. Okay, so this is all very different settings and very different assumptions, but they're all around exactly this. And so it says that the dimension of H0 M L to the K is, you just take and sum through F rho, sorry, I have to, it's unfortunate it's just so far down on the board, but F rho from over here, so the inverse image of this, you only take the regular points. So you only take the things that lie in the regular points of the torus, you divide by the Weil group, and then you take theta of f to the 1 minus g. So this is a very neat formulation of the theorem, which is due to Telemann and Woodward. And the speciality about that is that they proved this formula the following way. First, they proved that the higher cohomology groups are 0. So just want to remark this. So first one proves that this is the case. This was well known, and it's not a hard theorem. It's basically Kodaira vanishing in these moduli spaces. One just has to check the Kodaira vanishing actually works. It works because these moduli spaces has rational singularities, and therefore you can apply it. And now this means that this is the index, and then you can apply the Tillerman and Woodward index formula to compute it, and you get this. Okay. And it fits very well. You can check actually for SL2C that I gave you here, that if you stick everything together, you actually see the two formulas match. Okay, so now this is all, as I said, in some sense, old hat. So these are the old Verlinde formulas. So what we want to try to do now is generalize it. And sort of in the spirit of these days and this conference, what we're going to do is add another parameter. So we're going to deform it. It's not refined, but it's deformed because I don't think this parameter is the same as the parameter we heard about yesterday. At least I've had some communications with people. But I should say from here on, what I'm going to tell you about is joint work with Sergei Gukov, and Dupay. And these two guys know very well about these indices and so on, and they tell me it's not the same T. And so does Pavel, and I think Qumran also said that. So, okay. But what we're going to do is we're going to do something that's very, very natural from algebraic geometry, and that is just take this moduli space and replace it by the Higgs bundle moduli space. So we're just going to let MH, this is going to be the moduli space of semi-stable holomorphic Higgs bundles. And of course it's G Higgs bundles. So it simply just pairs P and phi. So P is this principal G bundle over X, which is holomorphic. So that guy is what we looked at there. But what we are adding is this Higgs field, and this is simply just a section over X of the canonical bundle tensor the adjoint bundle of P. So we just add a field like this. And now the semi-stability condition will actually depend on this Higgs field here, okay? But again, this is an algebraic variety, but it's not a complex algebra. I mean, it's not a projective algebraic variety. So it's non-compact, for example, as opposed to the other guy. So in fact, as an open dense subset, it contains the cotangent bundle of this guy here. Because if the principal bundle is semi-stable, sorry, if it's stable, then this vector space here is exactly the cotangent fiber to M here. And so that's the idea of why this inclusion exists. It's a little bit more complicated when you have to check semi-stability and so on, but it works. Okay, but it's bigger. All right. So now there is also, I'm going to use the same letter. There is a determinant line bundle. So that construction goes over without any change. So I have this determinant line bundle. And now what we would like to do is consider H0 MH L to the K. Well, okay, this is infinite dimensional. So what do we mean by the Verlinde formula? But that's where we're going to see the new parameter. Because there's one extra very nice feature that this space has. Namely, there is an action here of C star. So I can multiply the Higgs field by a non-zero scalar. This will not affect the semi-stability condition. And therefore, I have actually a C star action on this. And so therefore, I actually get induced a C star action on this. But okay, that means that I can take this space and break it into the isotypical components under the C star action. And it turns out that there are no negative terms, so it becomes a sum, L equals 0 to infinity, and then you have H0 mh L to the k, and then up L here, and this just means the subspace under which the C star action acts as the Lth tensor power of the identity action of C star on C. So this is the eigenspace decomposition according to the C star action. These guys are finite dimensional vector spaces. And therefore, I can now define what we call the Hitchin character, because Hitchin was really the guy who introduced these spaces, and I studied them a lot. And somehow it's really become a huge industry. So we define the Hitchin character. So dim T H0 MH L to the K. This is simply just a formal, for now, generating series of these dimensions. 0 MH L to the K, and then the Lth part, and then T to the L. Okay, so what I want to do now is I want to define or give for you what is the Verlinde formula for this. And now it makes sense to talk about this, because what I now want is I want a T-series that gives you all these numbers. Okay, so maybe I take this here. And so this actually goes by inventing a certain T deformation of this picture here. So the first thing we deform is the map chi. So we've deformed chi to be chi times, and then the following gadget. You take the product over all the positive roots, and then you take 1 minus t e to the alpha divided by 1 minus t e to the minus alpha to the alpha. So this means, if you apply this to f, take this and apply it to f. Take the log of it, multiply it onto alpha, and exponentiate. Then you get a map to the dual. There was a star missing here. So that's the T deformation of that. You didn't complain about what theta was, but theta of f is actually delta of f squared divided by the size of f. Sorry. So theta t of f is 1 minus t to the rank of g, 1 over the size of f again, and then the product over all the roots, and then 1 minus e to the alpha, 1 minus t e to the alpha, divided by the determinant of h dagger t. And h dagger t is the endomorphism of T induced by the Hessian of the following function. So the Hessian HT of the following function, d of psi is, well, first the quadratic term that you expect in order to recover. So if you take, well, let me just finish what I want to write. The trace in the Lie algebra, Lie2 of t e to the xi, and then plus rho xi. So when you consider this function here on the torus T, you look at its stationary points. That turns out to exactly be the inverse image of this of the Weil vector. And then you compute the Hessian at those points, turn it into a quadratic form, and you take the determinant of it. So let me come back to the remark I want to make before. So once we have done this, the theorem is, so this is with Gukov and Pei, the dimension of this guy here, this is summing f in f rho comma t regular divided by the Weil group. I'll introduce this just now, and this. So let me just, I mean, the f, let me do it up here. So f rho t is simply chi t inverse of, again, the Weyl vector. So if I turn off t, I will see that this goes away because there's a t here. This is just a linear term, so it doesn't matter as far as stationary points are concerned. I get this term here as the determinant to the power of this, and that's exactly what fits with the number f that I have. And so, well, let me not go through all the details, but it's very, very easy to see that if you turn off t in this formula, you get the old Verlinde formula. It has exactly the same form, just everything has now been t deformed. So that's equal to this. I should say that here g has to be strictly bigger than 1, and of course k has to be a natural number. Now, yeah?
Again, what the middle term in E of psi is?
This?
E of psi, the last line.
Sorry. Yeah, it's the trace in the Lie algebra, the dilogarithm, yeah, Li2 of t e to the psi. Okay. So, let me now tell you something about the proof of this theorem here. So, as I was saying before, you know, in the old-fashioned case, like the one I'm going to rub out here, it all relied on factorization, except for the Tillerman-Woodward stuff. That was just using an index theorem. So therefore, that's the only thing that's available right now, because we have not studied these spaces before. It's actually amazing that we haven't really done that. It took us 30 years to come from the compact space to the Higgs boson moduli space. But we haven't really studied these spaces here, and so in particular, we don't know how they behave when the curve degenerates to a nodal curve. What these formulae here strongly indicate is that they satisfy a completely similar factorization to the other ones. But we don't know that yet. So we have to proceed differently. So let me just give you the key sort of parts of the proof. The first part is that, well, the first thing that you will run into is you will just try to emulate the Tillerman-Woodward proof. So you will try to prove that the higher cohomology group, so this is 0. That's not true. So that will have some problems. So if you look at this, well, there are actually examples where this is not 0. So this is not 0 in general. So, well, how do I say this? It's of course sometimes it's 0, but it's not 0 in general. However, there is a very important lesson to be learned here, and that is the following: that if you instead introduce MH to be the stack of G Higgs bundles. So there's a beautiful theory developed about this, that these are really forming nice algebraic stacks. It makes sense to talk about line bundles on these stacks. It makes sense to talk about H0 and everything. And the nice thing about the stack is that you can actually prove, and so this is a theorem which is first of all due to Tillerman, but we have an alternative argument to this, and well, you'll see in parabolic case something else. So what we prove is that the higher cohomology groups over the stack of this bundle is really 0. So therefore, we actually have to go to the stack. Well, okay, now we've changed the problem, because now we have the stack. So therefore, we have to say, okay, well, what about the H0s? Well, the second part is that when you look at H0 over the moduli space of L to the K, then this is isomorphic to H0 over the stack. And here we're really using that G is bigger than 1. So this is not true for the other genuses. Okay, so that's very nice. So now we turned it into a problem on the stack. And then the great thing is that the Tillerman-Woodward index formula is really for the stack. So now we're just ready. We can simply just apply Tillerman-Woodward. index formula. And so this is simply the way that we came up with this complicated expression here. Well, I should say that you could have come up with it this way, because my physicist friends knew it from index computations, but it turned out that this one fitted exactly what you needed in order to get the right characteristic classes in the index theorem of Tillman and Woodward. And so therefore, when you do exactly this combination, you get exactly the output of the Tillman-Woodward index formula, and therefore you get this result here. Okay, so that's as far as no marked points is concerned. Okay. But what about marked points and so on? Because in the old-fashioned theory, the whole thing was organizing into a 1 + 1 dimensional TQFT. It was really beautiful, and it was all governed by a Verlinde algebra. So maybe that's the same here. And indeed, actually, it is. So let me just... But, however, what one really has to do, well, maybe I just delay that remark. So what I'm going to do now is introduce the parabolic moduli spaces. So now I let pH be the parabolic moduli space of semi-stable Higgs bundles. Okay, so this here really requires that, of course, that we have this x, this finite number of points in x, I mean really to the n, right, minus the diagonal, and you have to have these label set also. So you have labels, and now you have marked points. When you have specified these labels here, they precisely give you a well-defined parabolic, a moduli space of parabolic Higgs bundles. It's again an algebraic variety, and there is, given the level k, which by the way we have already fixed because the space here really depends on the levels, the labels, there is also an LK. It's now not a kth power anymore, but there is, simply meaning that this bundle does not have a kth root always. There is a determinant line bundle, and therefore we can consider H0 of the parabolic Higgs bundle moduli space L to the k here. So this it turns out that the Picard group, so there is sort of a similar discussion like this here, and it turns out that this is actually an isomorphism of Picard groups, and then the Picard group of the Higgs bundle and both parabolic and non-parabolic moduli space is the same as the Picard group of M.
Can you say again which space depends on K?
The pH here, because it depends on the labels, and the labels depends on K. Mm-hmm.
Is the label set the same?
Yeah, absolutely no change. No T depends on the label set.
So if you're doing complex transaminase theory, you would expect much more general labels.
Yeah.
But this story is most natural when the level of the actual complex transaminase theory, one of them is set to 0.
Yes.
And maybe that's what's...
Possibly, I agree. This here is this is relevant for complex transaminase theory when the imaginary part of the level is 0.
Yeah.
That's right. So
maybe that's trivializing all of the...
Yeah, I know. Certainly, but this is hard enough for now. It's for us at least. So, so we consider this guy here. We can do exactly the same, but we are thinking about that. So we can do exactly the same. We take and decompose it according to the C-star action. These are finite dimensional complex vector spaces. And so we can define the same way the parabolic Hitchin character to be exactly the same way. Dim T of this guy here, LK, is simply just generating series for this guy dimension of H0, pH, LK, L, T to the L, like this. And now we would like to capture this guy here. And we need one more piece of leaf theory that we had to figure out. Maybe I just remove this one here. So we needed to do a deformation of the characters. And there exist quite a few already. But somehow we were able to derive this ourselves, and then we found some correlation with Hardy-Littlewood polynomials, but I'm not going to talk about that right now. I'm just going to give you the expression. So if you take capital theta lambda, where lambda is any guy in the label set of f, so it's going to be a T deformation of the usual character formula, and so this is simply just the sum over the Weil group of the group. It is usual minus 1 to the length of w, e to the w applied to lambda plus rho. Then you get delta, and then you get product over the positive roots, and then you get 1 minus t e to the w of alpha, like this. And all of this is of course applied to f. So this is also applied to f, like this. So this is the deformed character formula, and then now you can easily imagine what the theorem says. And so this is again joined with Gukov and Pei. And so the theorem says that you look at H0 here. Also, again, I have to assume that the genus is bigger than 1. I'll come back to that in a second. The Hitchin character is simply given by sum over f rho t regular divided by the Weil group. You take theta t of f to the 1 minus g, and then you take the product I equals 1 to n theta lambda I of t of f. So that's the Verlinde, the T-deformed Verlinde formula for parabolic Higgs bundles. Okay, and the proof.
These are different thetas in the.
Yes, I'm sorry. This is supposed to be capital theta that was here. Thank you. So this is the deformed character formula, and this is the quantity that was before. So it turns out that we can take this proof here and recycle it completely, and simply just write pH here. The interesting thing actually is that it's a corollary of this, that although the higher cohomology groups on the moduli space are not 0, they don't contribute to the index. They cancel. So you put pH here. So here you do the stack of parabolic G Higgs bundles. In that case, so if we want to write it down here, so Tillerman didn't consider this, but we considered it, and the same arguments can be applied, and you get the vanishing over the stack. You also get the isomorphism on moduli spaces for H0 only between the stack and, so I guess I'm sorry, I'm now starting, so I guess I should use beta for the stack here, so let me do that to distinguish it from the space. So here is the stack, and here's the space. And again, so there's a way to first consider. So the beautiful thing about the stacks is that many of the things that don't work for the moduli spaces actually work for the stacks. So the technology is more complicated, but the algebraic geometry fits much better with it, or the algebraic topology, the link to algebraic topology. So in particular, the stack of parabolic G Higgs bundles is a principal bundle over the stack of just bundles. And therefore you can first compute it using the usual spectral sequences for vibrations, and then you compute with an index formula over the stack of bundles. So you can use the same Tillerman-Woodward index formula to actually prove this formula here as well. So this just comes from the contribution from the vibration, and that comes from the index formula. Okay. So let me just try to use the last 10 minutes to tell you about TQFT of this picture.
So just for a sphere with lots of punctures, is there a nice expression?
Yeah. Comes now. So I was just being very careful when I wrote g bigger than equal to 1. Okay. So it's I think the only thing that you need to know is that the Euler characteristic is positive for this to work. But I have for now a better remedy of this, because if you do the following. Namely, if you define, so if you take the Hitchin character, but you take the parabolic, you take the stack, then this is always equal to dgn lambda 1 up to lambda n, where dgn lambda 1 up to lambda n is just given by this formula. Rho comma t divided by Weil group theta t of f to the 1 minus g, and then this product. So if you define these numbers this way here, then it is always true that this holds, no matter what the genus and the number of punctures is.
So what was beta?
Beta is the stack. So if you replace the parabolic moduli space with the stack. Sorry. This is not right. Well, I can make this right by saying that if you take the Euler characteristic, so if you take 2g minus 2 plus n, if this is positive, then this is right. There are exceptions if this is not the case. But I can make it absolutely right, always, if I here write the index over the stack. So, I mean, let me write it down here, that the index, the equivariant index over the stack, and that's the guy that is absolutely equal to this physical index always. This is exactly this, no assumptions at all. So that's part of the theorem. So two parts. So the thing is that if the Euler characteristic is what am I saying? No, that's right. It's minus the Euler. So if you want H0, you have to make that assumption. But if you really want to see the full TQFT, you have to take the index. It turns out that there are higher cohomology groups when you have positive Euler characteristic. And I'll show you some of them right now. Okay. But so, the nice thing about this is that the index actually forms a 1 plus 1 dimensional TQFT. So, the next theorem says the following. That so the dgn is a 1 plus 1 dimensional TQFT. And if you like, the spaces here is a categorification, of course, of that. And so that means that if you look at dg plus 1 n lambda 1 up to lambda n, then this is, so you consider a factorization where you reduce the genus, then this is the sum over the label set. And then you get dg n plus 2 lambda 1 up to lambda n mu dagger, and this is the usual dagger from the old theory, so just a dual representation. But there is a correction term here, d mu of t. And all of this is, of course, a function of t. And d mu, so let me write d mu up here. D mu is inverse, is the Poincare polynomial t half of b G lambda. So the G lambda is the stabilizer of lambda inside G. You take the B of that, and you take the Poincare polynomial of that, and take the inverse of that. And that's the correction factor that goes into the usual factorization rules. And likewise, if I take G1 plus G2, N1 plus N2, I take lambda 1 up to lambda N1, lambda 1, 1, 2, lambda 1 up to lambda N2, 2. So now I have in mind that I want to split it so that half of the punctures go to one side, the other half of the punctures go to the other side, and I just split it along a guy that's separating, so the genuses just add. So I get I get sum over the label set, again mu, and I have G1, N1, lambda 1, lambda N1 of 1, and then you add mu there, and then G2, N2, and lambda 1, sorry, lambda 2, 1 up to lambda 2, N2, and then mu star. And then again, d mu. This correction factor for the gluing. It just means that the metric is different. The metric has this, it's not diagonal in this basis. The metric has this t-deformed behavior. So, let me see. So maybe I take this here and just introduce the Verlinde algebra. So the nice thing about this explicit formula is that you can actually see from this explicit formula that the right-hand side is analytic in T. So in a small neighborhood of 0, so if you look at the expression over here, it's analytic in T, and so it really gives you a one-parameter family of of TQFTs based on the same usual label set that you have from the old theory. And now you can simply introduce the Verlinde algebra. And so it's just going to be the usual thing. It's a finite dimensional vector space, but it's a Frobenius algebra, and this Frobenius structure is a product and an inner product, and they of course now depend on T, but it's a one-parameter family of such, and you know, lambda star T mu is simply defined the usual way. So you say D03 lambda mu mu star d nu, and then times nu, and you define this guy here, the inner product between these two, to be d lambda, like this. And so this here is indeed, so the theorem AGP is that this is a Frobenius algebra, finite dimensional Frobenius algebra.
Connect with delta.
Indeed, thank you. So this is a Frobenius algebra. This is a one-parameter family of finite dimensional Frobenius algebra, which completely, this is the usual classification theorem for TQFTs in 1 + 1 dimensional, right, which completely determines all these d, g, n's, the whole, the numbers, right? And so maybe these formula here looks a little sort of scary at first. You know, there are many sort of Lie theoretical things in it and so on, but maybe I can just over here in the end give you, because this means I just have to give you the Verlinde algebra for SL2C, and then you know how to compute all the dimensions.
Is that some special instance of given Peltian structure? Say that it determines the...
No, this is much simpler than that. This is just, you know, if you have a 1 + 1 dimensional TQFT, it's classified by finite dimensional Frobenius algebra. This is maybe Tureyev or something like that, 25 years ago. So, example. And I think you like this because you recognize if you take t equals 0, you see the old story, of course. So the inner product, this is delta lambda mu, because for SL2C, the dagger is trivial, right? And then you get 1 minus t squared and 1 minus t squared. And this is if lambda is 0, and this is if lambda is k, and else it is 1 minus t. So that's the way the inner product deforms. Normally it's just 1, 1, 1 all the way down, right? And then the fusion rules is the following. So f lambda 1, lambda 2, lambda 3, this here is the usual one if the lambda plus, the sum has to be even, as we know from the old theory, but then you have to have delta lambda being negative. And then normally, delta lambda I'll show you in a second, but it's the usual thing. And else normally you would say it's t, but it's not, sorry, it's 0, but now it's delta lambda half. And this is if this guy is even and this guy is positive, and else it's 0. So that's just in case lambda 1 plus lambda 2 plus lambda 3 is odd. And delta lambda is simply max of d1, d2, d3, d4, where di are the usual things. So d1 is the sum of them, minus 2k, and then the rest you know. So you know this one as well. So this is lambda 1 minus lambda 2 minus lambda 3, and d3 is lambda 2 minus lambda 1 minus lambda 3, and d4 is lambda 3 minus lambda 1 minus lambda 2. So you see it's totally explicit, right? So this gadget will always be even when I apply it. So therefore I get just t to some power, or 1 or 0 in this case. And now I can just work out, by using this factorization rules that I see up here, I can work out the dimension explicitly to any genus and any number I want. So it's actually rather computable. Okay, so thank you very much.
Questions?
Yeah.
Is there a natural pairing, like in TQFT, usual TQFT case?
What do you mean by pairing?
Yes.
Oh, the inner product.
The deformation of the Hermitian pairing you have in TQFT.
Yes, well, so I would say the first question ought to be, is there a projectively flat connection? I mean, because what you want to actually do is to show that this actually gives you a TQFT in 2 plus 1 dimensions. And so I don't know quite the answer to that. I know the answer to that in a different model where you quantize with respect to real polarization instead of using algebraic geometry. But I think the answer should be yes, there is also a connection in this case here. And then most likely there's also a pairing.
Is that the class group action easier to understand? Or?
Yes, the Markov class group action is yet to understand. So I don't have yet a projectively flat connection in these bundles here from the point of view that I presented here. I have a different one where I use a real polarization, but it's not totally obvious how to go between the two. I mean, there's some technical details in this, but it looks very likely that all of this will work out exactly the same way as we had the old story, and the whole TQFT just T deforms. But this is special when the level is real, because in complex transformance theory, there's no reason why you should take the level to be real. You should really take it to be a complex number. And as soon as you turn on the imaginary part, as Tudor remarked, the whole theory changes its nature radically. And it leaves, in my mind, big questions open for algebraic geometry. But I think it would be a very interesting theory, and we're trying to work it out, but we haven't understood it yet. But this one here is sort of completely understood now, at least from this 1 plus 1 dimensional point of view. And it would be nice to see how it gives a T deformation on a TQFT. And then possibly, add another parameter which is refinement also, because that could come on top of this, right? That's another story. In fact, one could think of adding many parameters, because the Verlinde algebra is big. And another question for the topological recursors is, are these numbers given by topological recursion? So it would seem very likely that they are, because together with Gaëtan and Nicolas, we proved that the old-fashioned Verlinde formulas are given by topological recursion. And the only thing that stops us from generalizing that to this case is that we don't know this factorization at the boundary. As soon as we know the factorization of the boundary, the constructions we made then will apply in this case here, and we'll get that they're given by topological recursion. But that's still open.
Excuse me, if you restrict to the genus 0 with pods,
Yeah.
usually you have a ribbon structure encoded in this.
Yes.
You see this?
And that translates to having a projectively flat connection over Teichmüller space of genus 0 and that number of points. And so, no, I don't know. Yeah. It's a very good question. It's the next thing on the mathematical shopping board. But you know, the old story also started with the Verlinde formula first, right? I mean, somehow the dimensions are easier to handle in the beginning.
So in this example over here, can you explain explicitly how the ring structure, the multiplication on the algebra deforms as you turn on t? I mean, is that easy?
Yeah, I mean, you see it right here, right? Because these are the structure coefficients. F here is that coefficient. Sorry. So this is F. Maybe I should.
I mean, if I didn't want to write a formula, but to think about like what the isomorphism type of the ring look like.
Yeah, so I don't know if this is complete answer in any way, but what I can say is that if you, for example, look at H0 over the moduli space of Higgs bundles, L to the k, then this here is equal to H0 over just M. And then you take ST of the tangent bundle. So you take the symmetric algebra and you put T in the grading. Tensor L to the k. So this is an algebraic geometric way of saying it. So when T is turned off, you don't see this at all. But when you turn T on, you get all of these symmetric powers of the tangent bundle coming in and deforming, you know, so here are the vector spaces that categorize these numbers, right? And so therefore, this is what contributes to the higher powers in the product. And so it comes from symmetric powers. And there is no first guy, because there are no vector fields in the moduli space that are holomorphic, but there are quadratic differentials, and so on. But when you turn on K, there are also those, and so on. So I don't know if it's sort of an answer, but it's something I can say in this direction.
Just to comment, it seems that the obstruction to lifting this to a full 3D TQFT is that the symmetry you're using to grade everything is not present on a generic 3-manifold. It requires the metric to have a product structure.
I mean,
surface times.
Right. From this index point of view, that's right, and that's also why, you know, it's so. When you use a real polarization to quantize, you lose the T action. And so, therefore, I think that the T deformation of the whole TQFT is rather intricate, because it's not like you can imagine that the whole thing factors, and then your flat connection will commute with the T star action. And that's sort of what you are indicating, right? So that would mean that the whole...
It might work locally, but not globally.
Yeah, so you know, it works when you have a 3-manifold with boundary and you have some cylindrical end, then of course you can have the structure. But if you have a general 3-manifold, it won't have the structure at all. It won't have the rotation action. But so the point is that if you take these direct sum of these spaces, you can still imagine that there is an infinite dimensional TQFT involved, and that you have a connection there that gives you a projectively flat connection, and it just has a very intricate way of interacting with this t action. That could still be possible, and I think that's what is actually happening. Yeah, I agree.
All right, excellent, Jorgen again.